In this circuit, our input is U of t, this current source, and our output is I of t, the current through the 3 Henry inductor. We want to sketch the magnitude response for this circuit. So we want the magnitude of h of j omega as a sketch, which is the magnitude of the output as a function of frequency over the magnitude of the input as a function of frequency. Probably the easiest way to do this is to use the circuit itself to calculate the low frequency gain, the high frequency gain, and the corner frequency. Take a look at the circuit as omega goes to 0. So at low frequencies, the inductor looks like a short circuit. So we have this 2 ohm resistor. Converting it to the frequency domain, we have an input phasor as a function of frequency, which at 0 frequency is U of j0, a 3 ohm resistor, and at low frequencies, the inductor looks like a short circuit. So the current through this leg is I of j0. This just looks like a current divider. So this is U of j0 times the other impedance, 2 ohms, over the sum of the 2 ohm and 3 ohm impedances. So dividing both sides by U of j0, h of j0 is 2 over 5. At high frequencies, omega goes to infinity. We redraw the circuit. There's our 2 ohm resistance. The input becomes a current phasor U at j infinity, a 3 ohm resistor, and at high frequencies the inductor looks like an open circuit. So I of j infinity is equal to 0, which means that h of j infinity is just 0. Now we can start on our sketch. Horizontal axis is frequency in radians per second. Vertical axis is magnitude of h of j omega. At low frequencies, when omega is equal to 0, this is 2 over 5, and it goes down to 0 at high frequencies. Now we need to fill in the corner frequency, or the cutoff frequency, omega sub c. The magnitude at omega sub c is the maximum value, 2 over 5, times 1 over square root of 2. So there's our magnitude. Now we just have to find the frequency. It's probably easiest to notice that for a first order circuit, omega sub c is 1 over tau, and for an RL circuit, tau is equal to L over the equivalent resistance. So if we find the equivalent resistance seen by the inductor, have a 2 ohm resistor. If I kill the current source, it becomes an open circuit, a 3 ohm resistor, and then across these terminals is where I want Req. By definition, there's no current through an open circuit, so these two are in series, and Req is just 2 ohms plus 3 ohms, which is 5 ohms, which means that tau is 3 henries over 5 ohms, or 3 over 5 seconds. Omega sub c is 1 over tau, so this just becomes 5 over 3 radians per second. There's our sketch, and officially we're done. However, where possible, you always want to check your results by doing the problem another way. So I'm going to go to another slide, calculate the frequency response, and double check my magnitude response values using that. So I'll convert this circuit to the frequency domain and calculate h of j omega, which is going to be the output phasor as a function of frequency over the input phasor as a function of frequency. I have a 2 ohm resistor. The input becomes a phasor, which is a function of frequency, with 3 ohm impedance, and the impedance of this inductor becomes j3 omega. The output phasor is I of j omega, which is still the current through the inductor. This still looks like a current divider. If I combine these two impedances in series into an equivalent impedance, 3 plus j3 omega ohms, then I know the total current, U of j omega, going into a parallel combination consisting of these two impedances. I can easily find I of j omega. So I of j omega is the total current, U of j omega, times the impedance in this leg, which is 2 ohms, over the sum of this impedance and this impedance. 2 ohms plus 3 plus j 3 omega ohms. H of j omega is, if I divide both sides by this, 2 over 5 plus j 3 omega. Now I can use this to find the low frequency gain, the high frequency gain, and the corner frequency. So H of j0, just plugging in 0 for omega, is 2 over 5 plus 0, which is 2/5. So the magnitude response at 0 frequency is 2/5, which is the same answer we got before. H of j infinity is 2 over 5 plus infinity, which is just equal to 0. So the magnitude response at high frequencies, j infinity, is equal to 0, which is also the same answer we got before. I can find the cutoff frequency from this pretty easily by putting this equation in standard form. If I write H of j omega as some constant over j omega plus omega sub c, that lets me pick omega sub c out directly from this. So I need to divide out this 3 to get the j omega term like this. So this becomes 2 over 3 over 5 over 3 plus j omega. So this is omega sub c, which also agrees with what we got before.